Chapter 1, Exponential and Logistic Models, Part 2. Here we're going to look at the logistic growth equation. I of t equals k over 1 plus k minus I0 over I0 e to the minus RLT. In this case, k is a maximum infected population. I0 is the initial infections at t equals 0. T is equal to time in days, like we said before. Can be any time unit, but days is the most convenient. RL is the logistic growth rate, and I of t is the number of infections in time t. One thing to keep in mind is this fraction here is just a numerical coefficient. So once we know k and I0, we can simplify this model down considerably. One feature of logistic growth is this sets a maximum value at k and it never exceeds it. So that's one advantage we have with logistic growth versus exponential growth. So we're going to return to a previous problem of we have 10 infections and it's going to double every 3 days, except for we have this add-on here. The maximum infected population is 10,000. So that could be 10,000 could be a suburb of a city, and suppose we had a wall around it and people kept to themselves and we introduced 10 infections to do an interesting experiment. And we're going to set up the logistic model like before. Here we have 3 parameters to consider: k, I0, and RL. Once we find k, I0, and RL, we're all set. We can set up the logistic model. 2 other parameters usually given. Doesn't have to be. You can come up with all sorts of interesting math questions where this information is indirectly given. But we're staying simple. This is a course for beginners. So first of all, k is equal to 10,000. And also I0 is equal to 10. So we can substitute that. You can get rid of a lot of these parameters. We have I of t is equal to 10,000 divided by 1 plus 10,000 minus 10 divided by 10 e to the minus RLT. So we plug these parameters in for k and I0. There's 2 different k's and 2 different I0s. Now, 10,000 minus 10 is equal to 9,990. Divided by 10 is 999. So you can simplify this equation considerably. 10,000 1 plus 999 e to the minus RLT. Then, of course, the only thing we're missing is RL. And like before, that tells us how fast the growth rate is logistically speaking. You have to know some data point in the future. It doubles every 3 days. So let's go ahead and figure that out. In 3 days, when we have t is 3 days, we have our infected population is equal to 20. So we can substitute. You get 20 is equal to 10,000 over 1 plus 999 e to the minus RL times 3. Another question is, how do we solve for RL? Well, you can multiply both sides by this factor, cross multiply, however you wish to do it. Let's erase a little bit of this. You have 20, 1 plus 999, e to the minus RL times 3, equals 10,000. Then if you divide both sides by 20, you have 1 plus 999, e to the minus RL times 3. 20 goes into this 500 times. we really want to isolate this exponential factor. And so we're going to subtract 1 from both sides. 999 e to the minus RL3 is 499. And let's clear a little bit of space here. Come back up here. You can always rewind the video. We're going to divide by 999, and that gives us e to the minus RL times 3 is equal to 499 over 999. And of course, we need to get rid of that e, so we're going to take the natural log of both sides. The ln cancels out the e. We get negative RL times 3 is natural log 499 over 999. Okay, the math here is a little more interesting, obviously. And interesting to work all this out on my little whiteboard in my upstairs room. Need to multiply by negative and divide by 3, and so we have RL is equal to negative natural log 499 over 999, all divided by 3. Now you can use a calculator to do this. And one thing to note, this natural log of a fraction is going to be negative. Negative times negative is positive. So we will get a positive number. And it ends up being 0.231. This, it turns out, under certain conditions is identical to the exponential growth rate. So, or close, I should say close. This is approximately our exponential under certain conditions. In one of the later chapters, we'll look at what conditions this is true. But suffice it to say here, as long as this maximum infected population is much greater than the number of initial infections, these will be the same to 3 significant figures. If we went out to the 4th significant figure, in this case the 4th decimal place, you'd find out that RE and RL would be different. So, and this gives us an interesting strategy. You know, if we were using exponential and logistic growth to model something, and logistic growth was a perfect model, this is not a perfect model. We'll look at the inadequacies later on in a later chapter. If this logistic growth was a perfect model, early on, and maybe you didn't know this K value. You had no idea what it was. It was a shot in the dark. You could first of all find this exponential growth rate, and then you could use, as time goes on, you know, let's suppose 2, 3, 4 weeks goes on, and then you could solve for this parameter K by using further data. So, and that's how mathematical modeling works. Quite often you have to be clever at figuring out these parameters. And that's just one way in which you could do it in this case. So, well, in any event, we have this. We should plug back into our model. I of t is equal to, on top is k, 10,000 over 1 plus 999 e to the negative 0.231 t. And that is our model. We could use that to make predictions. Just one further note. If you look up logistic growth, varying applications, sometimes they'll just get rid of this negative and make that positive. And you can certainly do that. If you make this positive, then down here RL would have been negative 0.231. So whether you build a negative into the formula or not, that's really up to you. It's just a matter of choice. So, okay, that's all for part 2. We'll be back with chapter 2 in shortly.